Hello guys, in this video I'm going to show you how to solve structurally unique binary search trees problem. So given a number n, write function to return all structurally unique binary search trees that can store values 1 to n. Right. So for example, if our n is 3, right, then we must find all binary search trees, all unique binary search trees that store value from 1 to 3, right? So let's see trees uh, what trees could be constructed from these three numbers, right? So the first one is, firstly we take the node 1, the value 1, right, and take it as a root node, right? So for tree that has one is root node, we have one, we have these trees and these trees, and remember that the characteristic of a binary search tree is that uh, the right subtrees, the values of right subtrees must larger than the root node, right? For example, if root is 1 here, then it means that all the values on the right subtrees must greater than 1, and all the values on the left subtrees must less than 1, right? So because, as you can see here, 1 is the first value here, so there's no any value that is less than 1, so it means our task is to just somehow, put 2 and 3 to the right of the node 1 here. So there are two ways to put 2 and 3, right? The first one is if the right child of 1 is 2, then node 3 must be on the right of 2, so that we have 3 greater than 2, right? We cannot put 3 to the left of 1 of 2 because it's gonna make our binary search invalid. And the second way to put it here is that I will put 3 as the right child of node 1. Right? In that case, 2 must be on the left of 3. Right? Okay. So we're done with 1 as a root node here. So if we take 2 as a root node, then here we have only one possibility, right? If 2 is a root node, then uh, our task is to somehow put 1 on the left and 3 on the right. So obviously there's only one choice here, right? Okay, so So finally, it will be 3 as a root node, right? So if 3 is a root node, same as the node 1 here, we have two choice, right? If 3 is a root node, our task is now put 1 and 2 to the left side of 3. Okay. Same here, we have two choices. Okay. As you can see here, we can delegate the original problem, right, to the like for example, if we are node 1 here, right? If we take node 1 as a root node, right? So in it means 2 and 3, it means all the values on the right of node 1 must be on the right of node 1 here. Okay, so in that case, our task becomes like how uh, our task at that point will be find all the binary trees from these values, from these two values, 2 and 3, right? So by delegate the uh, delegate the problem down to each child here, right? And at the same time, we narrow down the the values, right? So when we are at 1 here, the problem is find all the binary trees that can store the value from 1 to 3, right? But if we take 1 as a root node, then it means our problem is now only find all the binary trees that can store value 2 and 3, right? And we delegate it to the right child, and we will expect that this could return an array of all possible trees with these two values. So probably I will expect that the uh, the value that is returned to node 1 would be something like tree with root 2 and tree with root 3, right? So here is self EA3 by self EA3 with node 2 as a root node, right? And here by itself EA3 with node 3 is a root node, right? So, okay. So let's dive in coding to see how it's gonna be translated. Okay, so let's first write down some uh, some instructions here uh, to guide us. Okay, so probably because here our function takes in n, right? Mm, so it means when I call it recursively, um, I would, let's say, probably I will like need to run from 1 to n, right? And with, okay, with each run I, from 1 to n, with each I, I take I as, make I, so as a root node. Okay, what else? All the values from 0 to all the values from 0 to I minus 1, mm, should be put on the left side of root node, right? Because we want to put all the values that is less than the value of the root node to the left, right? And all the values from I plus 1 to n should be put on the right side of the root node. And as you can see here, here is actually a recursive call, right? That we need to solve. So this is probably gonna be something like um, find unique binary tree such as, but here uh, we need two values to, we need two boundaries here for the values. So and because the function signature here is only n, so because I want my recursive call to pass down more informations. There are two ways we could nest a private functions inside here, or we can pass it directly here, like from let's say start and end, right? Mm, but might be better to create a private function, not to modify the function signatures here. So functions, this is private, so I will mark it as a underscore by unique. Yes, see, this one will be called recursively. We need to two parameters uh, to limit the values. Like for example, here for the three values here, the index will be 0, 1, 2. So if uh, so if I want to build a trees, so for example, when I take the one as a root node and uh, I want to build trees from 2 and 3, right? On the right side of node 1. So that would mean it means these value will be from index 1 to index 2. So here we need to pass two index start and end. Okay, so I will bring this over. Okay, so here it will be I will start the I from start and I will run all the way to the end. I plus plus. Okay, here is run from I to N. With each I will make it the root node. It means I can do something like I could create a new node here, node, new node, and the value of this node is actually I, right? And now, okay, so let's say, for example, A, B, C, I, Y, Z. For example, Y is I is here, then all the values on the left of I should be put on the left side of this node. All the values on the right of I will put on uh, the right of this node, right? So at this point, I don't know that how to make binary trees from this value yet, right? So this is gonna be a recursive call, right? So it means I could find unique binary trees here, passing down what the limit currently is in I. So the start will be the same here, and the end will be I minus 1. And the second call will be find all unique binary trees from this value, and this value will be determined by the start from determined by start and end, and start will be I plus 1 because we don't take I here, and the end will be the end of this from end here. Okay, so I will expect that this could return multiple trees, right? Okay, so left trees, and here right tree. Like for example here, uh, if we take node 1 as a root node, right? So it means 2 and 3 will be on the right, and obviously here from 2 and 3 we could build 2 new trees, right? From 2 and 3, right? And we will return this array of 2 trees for the node 1. Okay, here's the lab trees. Here's the trees that we could build from these values, and here the trees that we could build from this value. Okay, so this will be an array, right, of all the root node of each tree. So I need to combine all the possibilities here. Okay, so one way to do that is to just use a nested loop here for lab child. As a lab root of lab tree, and for right root of right tree, and for one combinations uh, of one value from the left trees and one value from the right trees, we could build a tree, right? And this should be moved inside here, right? So that for each combinations, I will build a new tree, and not left is left root, not dot right is right root. Okay, and this will be one trees, one possible trees for the current functions, right? So it means I will need to store the values into an array, and if I successfully build a tree, I will push it into. Finally, I will return. Yeah. Okay. I will return it here. Down here, I will call the private functions, passing in the start. But the first function call will be 1, and the end will be n. Okay. Mm. So because here is a recursive call, so it means I need the base case. So when do we want to stop? So for example here, 1. Okay. So at 1 here, for example, so it means, for example, I here is 1, right? Then start will be from 1 to 1 plus 1 is 0, right? So 1 and n is 0, so it is when start is greater than n. It means in that case we don't have node on the left, right? We don't have the node. Uh, it means we don't have a node here. So what should I return here? Because we must follow these signatures is that this function will return a list of trees here. So here I must return a list of single value, which is null, right? So what I expect from 1 here to return from its left is a list of null, so that here the left trees will be uh, like this, and here I could check combinations, all combinations with 1 from the left and 1 from the right to make a choice, right? Okay, so here's the case. Start less than n. What about start equal to n? Mm, so it is when we have only one value, right? So in that case, we could right away view we could return uh, a list of only one node, right? So it will be new node. The value of that node will be start. Okay, that is the base case. Okay, run the test. Okay, it knows work or not. Okay, it works. So that is it for structurally unique binary search trees. Thanks for watching. See you in the next video.